Okay, guys, just before our last presentation, just to remind you all to please stay in your seats. We'll hopefully be joined by people from the security dome upstairs for the conference closure and the final farewell from the whole Hacktivity team. So our last presentation of the weekend is entitled, What's Common in Oracle and Samsung? They Tried to Think Differently About Crypto. Please welcome Toth, Laszlo, and Spala, Ferenc to the stage.
Okay, thank you very much. First of all, thank you for staying with us. This is the last presentation. So my name is Ferenc. My friend here is Laszlo. And we will talk about Android phone encryption, focusing on the Samsung devices. And we have a surprise, of course. So this is an intro slide about Hungary and about the Hungarians. But we are in Hungary now, so it makes no sense. So it's a good country full of smart people. We invented a lot of things like the Rubik's Cube, the ball pen, match, vitamin C, and things like that. We have beautiful girls as well. So we are working for Deloitte as a security consultant. So we do the usual stuff like penetration testing, security audits, vulnerability assessment, and things like that. And as you can see on the pictures, Laszlo has more experience than me. Means more blood on his T-shirt. Actually, he's my boss, so it's my blood on his T-shirt, so it's a sad story.
No, it's fun.
No, it's not. Okay, so just like last year, we have 4 different topics for you. First, we will take a look at the Android phone encryption and the Samsung phone encryption. What are the differences? Then we move to the Samsung SD card encryption, because there are some interesting things as well. And of course, we have a lot of tools. They are already released, so you can download them. And of course, we played a little bit Oracle again, because we love Oracle. So first things first, Samsung phone encryption.
Before we start, here is a warning for you. We conducted our researches on the following device models, S2, S3, and S4. And when we're speaking about this version, we speak about these specific device models. And we mean not only the specific devices, but their own variants too. Of course, we did not test all of the possible combinations like US and European firmware versions. But what's the point? Oracle supports disk encryption from version 3. Android supports disk encryption from version 3, which was the tablet-only version built. In case of phone, Android supports disk encryption from version 4. It's open source, the algorithm is well-known, public, it has been thoroughly analyzed over and over again, boring stuff. But Samsung thinks differently. To see the difference, we first need to understand how the normal way of Android encryption works. From a user-supplied password, the key is generated with the password-based key derivation function too. The encrypted disk key is stored in a file or the encrypted partitions footer. The encrypted disk key is AES decrypted. And in order to perform the actual encryption, Android uses the mcrypt, which is part of the standard-based Linux kernel. That's why it's easy to mount an Android encrypted disk under Linux. We will demonstrate this later in our presentation in case of the Samsung phone. The key derivation function uses 2000 cycle in theory, in practice is 4000. And the mcrypt uses AES CBC. Fortunately, this diagram is easy to remember because it looks like a desert eagle with a bullet.
Guys, don't give a gun to him. Never, ever, please.
I don't understand this, sorry.
Remember the blood.
Okay, this is how the encrypted disk is stored in the encrypted partitions footer or in a file. The key length is 16 bytes. This is the encrypted disk key. This is an IV used by the key derivation function. And I call this section padding, which will be important when we're discussing the Samsung way. In case of Samsung, the basic idea is the same. A key generated from the password and used to encrypt the actual encryption key. And the result is stored in the same file in the same file or in the encrypted partitions footer. The difference starts here. There are two hex constants. They are AES encrypted with the key derived from the password. There are two XOR operations. The first parameter of the XOR operations are the AES encryption results. The second parameters are the first half of the encrypted disk key and the second half of the encrypted disk key. The clear test key is the concatenation of the XOR results. Samsung also uses the encrypt with AES CBC, and the key derivation function uses 4,000 cycles in theory, and SAJ 256. The FIPS documentation helped me, but I had to debug ARM stuff a lot to have an idea about the details. Do you remember the Desert Eagle? Fortunately, this is also easy to remember because it looks like a Star Trek ship. Okay, the key storage didn't change too much. The main difference is the key length, of course, because it's longer. And the most important difference is the padding. It is not all 0 here. Let's go through some differences. The key derivation, in case of the key derivation, the theoretical number of cycles is bigger in case of Samsung. And Samsung uses SAJ 256, like Android SAJ 1. And the key length is used to encrypt the actual encryption keys longer in case of Samsung. So it's 256. And the padding is used for something. In case of Samsung, it is an HMAC of the encrypted disk key, not the decrypted, but the encrypted one, and the key derivation results. It means that in order to verify a password, you don't have to decrypt the actual encryption key. There is a password verification functionality built into the whole day process. On Android, the whole day process is responsible for handling disk, like mounting operation and disk encryption. When it started, a socket opened by the whole day process, and you can send command through this socket. The VDC command can be used to send command to the whole day process. The VDC is the part of the standard-based Android operating system. You can run it with root or system privileges. This is how can you send a command to the whole day. In the first case, we send the incorrect password. In the second case, we send the correct one. As you can see, or rather you cannot, there is no difference in the terminal output. However, if we check the syslog or the logging system with the logcat utility, we see on the first attempt the password was incorrect. This is how it works on S4, but it does not work on S2 and S3. And when I'm talking about the S2 and S3, I'm meaning their own variants too. But okay, so we have, as a result, we have an on-device password cracking engine. Well, terribly slow. So that's why I made the decision to look deeper into the Samsung way. On Android, the relevant function is called from the cryptfh.c of the whole day process. In case of S4, the verify underscore EDK is called from the libsec underscore kem.so library. Let's see how things work together on Android. It decrypts the encrypted disk key with the supplied password. The result is stored in the decrypted master key array. Then the decrypted master key array is compared to a saved master key, the clear test key. And there is a slow sleep call against brute force attack. Nice try, isn't it? But wait, we have a saved master key. Strange it may seem, but in the whole day process memory, you can find the clear test encryption key. Fortunately, the whole day runs as root, so you need root privileges to dump this clear test key. In case of Samsung, as I said, the verify underscore ADK is called. Basically, it generates a padding from the supplied password with the help of the key derivation function and the HMAC of the encrypted key and the key derivation result. Then it compares the generated padding with the stored padding. Cool. In case of Samsung, it seems, doesn't need the clear test key to verify a password. So it kind of stands to reason, do not store the clear test key in the memory. Unfortunately, it is not true in case of S2 and S3. And we have a live demo for that one.
Yes, so from this point, I'm the only one who can mess up this presentation, so cross your fingers, please. But before the first demo, we have a surprise for you, because we want to give you something special, and the most special thing in a hacker conference is a girl. Okay, it's not true in this room now, and thank you, all the ladies. So we have a special guest. Her name is Sandy. So guys, please welcome Sandy on stage. Yeah, she's cool. So she's beautiful. She loves hacking. And she does not talk too much. So she's the perfect girlfriend.
Take it easy. He has a girlfriend and I have a wife.
Yeah.
Just don't talk about them,
Yeah,
about Sandy.
yeah. Because we spent a lot of night with Sandy, so yeah. Okay, so for real, Sandy is a framework written in Python. And the basic idea is when Laszlo started to came up with his results, there were two ways. The first is to create separate scripts and programs for all of the results. And the other way is to create a framework. So we created Sandy. And of course, we made the first mistake of all programmers because we designed and implemented Sandy from scratch. So she's unique, let's say. OK, so for the first demo, we will use a S3 device. It is booted, encrypted, and the screen is logged with a password. So it's kind of secure phone, let's say. So let's start to use Sandy. As you can see, you have two main options. You can deal with phone stuff, and you can deal with SD card stuff. So we go for the phone now. And we choose the vol-d process thing, because Laszlo just talked about this. In case of every function or every module of Sandy, there are some parameters you should configure. But in most of the cases, you may leave the defaults, and it will work. So just leave the defaults. And yes, it's working, it's working. I can't believe. OK, so.
Come on, it's stable.
Yeah, it's full stable. So what happened? We just found the vol-d process. This is the process ID. We spot the relevant memory segment based on the procs file system. We uploaded a tiny binary. It's a memory dumper. It's precompiled. It's bundled with Sandy, so it's ready to use. So we uploaded this tiny binary. We dumped the relevant memory segment, downloaded the dump file from the phone. And this is the interesting part. This is basically a strings output on the given dump file. And if you take a look at the last line, whoa, so the last line, this is the clear text lock screen password. So Laszlo told you there is the device encryption key, but this is something else. This is the lock screen password. So I can use this password to unlock this phone. And after that, you can do anything for sure. But there are other green stuff. These are the device encryption key candidates, because it's not so easy to find the device encryption key. So based on the clear text password, position of the clear text password, you may find some candidates. But based on our testing, you may use the first one, and it's going to work. So OK, what's the point? What can you do with this device encryption key? Let's say you have a DD image from an encrypted phone. You can do it, for sure. And you can use this encryption key to mount that encrypted DD image. So let's try it. There is an option in Sandy called mount, surprise. And just make it up. And yes, I want to mount the DD image from a key file because I have a key file. This is the DD image. This is the key file we just saved seconds before. And the result will be mounted to the user data folder. So let's try it. As you can see, we use the normal crypt setup, so there is no real magic. And if we are lucky enough, if we check the user data folder, This is the mounted encrypted DD image in clear text. So it's kind of cool, or something like that. So let's go back to the show. Sorry, just 1 second. Yeah, to the show.
So besides the clear text encryption key, the actual password is also there. This works on S2 and S3. It doesn't work on S4. You need root privileges, as I already mentioned, and we use the Android debug bridge in our module. Of course, if you are already root, the game is over. So I'm sure several other methods can be developed to get the same information. But now you have one, and it can come handy in certain circumstances. But what if we do not have this level of access? We can still try the offline brute force attack. For an offline brute force attack, we need a recovery image with ADB in it and with a DD command in it. And we can use DD through ADB to dump the encrypted partition's footer, the last 16 kilobyte, and try to crack it. And we have an online demo for that one also.
Yes, demo time again. So we will use the same phone. Whoa. And now we go for this dump footer option to carry out a kind of offline password brute force attack. So let's dump the footer. Dump the footer. Default values are fine again. Okay. And here's a warning. So you may not use this module in a forensic situation because, as you can see, we upload something to the phone. It's a small binary, it's a seek and read binary to get the last 16K of the footer. Of course, you can do it with DD, but it's terribly slow. So we are talking about 9 or 10 gigs partition at least, and it takes minutes to seek to the last 16K because DD reads through the whole partition to seek to the last 16K. So this is why we have this small seek and read binary, but it modifies the phone.
Yeah. Fortunately enough, Sandy has a module that is able to dump this partition footer from a DD image. So if you have a forensic case, use that one.
Yeah, the name is dump footer from DD.
Yeah, it's very hard to remember.
Yeah. Okay, so we have the last 16 key of the partition, so the footer. So what's next? We are going for an offline password brute force attack. So let's convert it to John the Ripper format because we love John the Ripper. And it may look familiar with you. It's the standard John format. The only problem is, if you take a look at the current John version, there is no support for Samsung encryption. On GitHub, you may find a module for Android encryption, the stock Android encryption. It's not in the release, not in the Jumbo version, but there is nothing for Samsung. So Laszlo had to develop a new Samsung John plugin in order to be able to crack the Samsung encryption encrypted password. So this plugin called SendCrypt, and in this case, we will use a dictionary file because we have a so complex and so secure password, so it would take ages to crack without the dictionary file. So let's try it. And yes, we just cracked the encrypted password with John. As you can see, it's really secure. This is our favorite password, by the way.
Yeah.
So,
we are using it on Gmail, so please don't try it.
Yeah, no, that's capital Q.
Yeah, okay, it's capital Q,
Yeah.
so please don't try it.
Okay, so whatever. So we just cracked the password from the footer file. So it's kind of offline brute force attack. So go back to the presentation. Oh, yeah. Yeah.
Okay, so if you know the algorithm, it's fairly easy to develop a brute force for it. I chose the John the Ripper platform. This was my first John the Ripper module. By the way, I was astonished how easy to develop or add a new module to the Jumbo version. The module is far from being optimized. For example, I didn't develop the OpenMP support yet. 1.8 version of John the Ripper supports the parallel running for all modules. Unfortunately, it hasn't been ported to the Jumbo version yet. It's kind of slow because of the 4,000 cycle in the key derivation function, just like in the case of the WPA pressure key authentication of the wireless world. Samsung has a password policy when you set up the encryption. However, it's not a strong one. So we think on a CPU, a dictionary attack against the weak password is still feasible. We are sure you can develop a faster solution on a GPU. And we assume on a GPU, a brute force attack is still feasible against the weak password. So the moral of the story is that the weakest link is always the user, and even weaker when it comes to mobile devices. Just try to type in a complex password into a mobile device, like dancing tango with tight feet. But this method doesn't work on S4, because with S4, Samsung went further. The key storage is changed, the key length is the same, but now we have an encrypted footer. Sorry. ARM introduced a trust zone into its CPUs, a trusted execution environment. As a rough definition, it is a hardware-separated execution environment. It is separated and protected from the normal mode calls. On Samsung phones, there is a kernel called Mobicore in this environment, which was developed by a German company called G&D. You can have trustlets above this kernel for a specific purpose. On S4, one of them is used for disk encryption. However, the Volday process is still there, and the VDC command can be used. The Volday sends the data from the partition footer to the secure storage daemon. And the secure storage daemon communicates through the kernel drivers with the help of a client library with the Mobicore environment. Maybe that's just me, but this one looks like a glass of beer. The Volday process calls this function at the end of a chain to communicate with the secure storage daemon. It sets up an Android shared memory and sends the file descriptor of the shared memory to the secure storage daemon and uses them to communicate with the secure storage daemon. The secure storage daemon uses these functions from the client library to communicate with the Mobicore environment. There is a good analysis on the SensePost blog. How can you analyze this method of communication? The MC open session can be used to set up a session to a specific trustlet. The supplied UID can be used to identify the trustlet on the disk. In theory, it should be encrypted and signed, according to SensePost. When I check the strings in it, I receive back this snippet. At least some part of it is not encrypted. At this stage, I was very happy. I thought this will be an awesome research. But unfortunately, it can be solved in a very easy way. Yes, it will be a nice research in the future for somebody or for me. But now, I only need just an offline brute forcer. And it can be solved in a very easy way. You need a recovery image that runs the Mobicore environment. For that, you need the Volday process, the secure storage daemon, and the MC driver daemon. Then you should attach a debugger to the Volday process and set a breakpoint and the verify_edk function. Then you should initiate a password verification with the help of the VDC command. Then all you need is just dump the first parameter of the verify_edk function. And we have a live demo for that one also.
Yes, for sure. But first, I have to clean up a few things, so give me a second. I just restart Sandy. I will tell you why, but she's a girl, so sometimes, you know.
You have to be gentle.
Yeah. Okay. And the most important thing, I have to change the phones. So this time, we will use an S4, the new flagship device of Samsung. It is booted into this special recovery mode, but it's not a big deal because most of the Samsung phones can be booted into any recovery. So yeah, connect to Mac. Just, whoa, it's an expensive one, so stay up here. Okay, so just let me try it. Oh, okay, perfect. So go back to Sandy. So we are still go for the phone stuff, and we use this S4 module of Sandy. Default values are fine again. Oh, it's working. Okay, so,
I said it's stable.
yeah. Okay,
I
so,
am the boss. Hey.
yeah. Okay, so, the story is we uploaded the GDB server to the phone. Again, it's precompiled and bundled with Sandy, so nothing to do with this. We uploaded the GDB server, we started the GDB server, and we connected to this GDB server from the machine, so it's a kind of remote debugging. In Sandy, there are two versions of precompiled GDB clients, one for Kali Linux and one for Macintosh. So you can use them. And then we just find the VolD process, attach to the given thread of the process, set a breakpoint to the verify_edk function, and we just initiate a password verification with any password, it doesn't really matter, 1, 2, 3, whatever, to hit the breakpoint. And when the breakpoint is hit, we need the first parameter. But you have to remember, this is ARM, so you need the R0 register to get the pointer to the first parameter, so we just dumped the first parameter. And as a result, we have this John format encrypted password thing again. And of course, we have the footer as well. So we have two results in this case. So what's next? Again, we can use the same join module in order to crack the encrypted password from an S4 device as well. So I just show you we are not cheating. We use the same join module, but we use the S4 password now. Okay, it's tricky because we use
our Gmail password.
and our Gmail password. So it's tricky because we use the same password on the in the S4 as well. But believe me when I say this is from the S4 device. So we have the password, and we can use this password to mount an encrypted DD image from an S4 device. So almost the same story as in case of S3. So I want to mount, and now I want to mount the DD image from a password because I have a password. This is the DD image. And this is the case when you should change a default value because we are lucky. And the default value of the password parameter is our very secret password. So you have two options. Change the parameter or use this very secure password on your own device. Please use this password.
As a Gmail password too.
Yeah, as a Gmail password too. And Facebook, Twitter, you know, everything. Okay, so let's mount it. The same crypt setup stuff again. And if we check the user data folder, here is the encrypted DD image mounted in clear text. So you have all the files. Yeah, that's all from my side. So, okay.
Okay, so as you saw, the verify_edk function first parameter contained the encrypted disk key, which was in the same format as for S2 and S3. So the same encryption was used. So the same John the Ripper can be used to crack it. So what we can say, despite the trust zone and Mobicore magic, we still have an offline brute force capability. Cool, isn't it? But we did not stop here, because Samsung supports SD card encryption. And the most annoying thing with the SD card encryption of Samsung, you cannot use it in a different PC or in a different phone after you encrypted your SD card. So it's worth to dig deeper what's happening there. It uses the well-known encryptFS file system. It's the file encryption engine. Every file is encrypted separately. The encryption key is stored in this file. The format is the same as in the case of S2 and S3. The same algorithm is used, so the same John the Ripper code can be used to crack it. So it's boring, and we are not demoing this one. But what's wrong with this picture? For a beer. Anyone? Lajos, you cannot tell it.
Yeah, come on for a beer.
Yes, After, just look for us and you will get the beer.
Or something.
Okay. An S240C, the file which contains the encrypted disk key is word readable. An S3 and S4, it is protected. Only the root user can access it. But wait, the first S3s came with 403. The file is word readable on those phones. And if you encrypted your SD card before you upgraded your phone, the file is still word readable. My boss phone behaved exactly the same way. It received an update from Samsung. It is on 412, but the file is still word readable. On the right side, you can see a screenshot from a zero privileged application that shows the content of the file. So a malware can steal it. The first 8 bytes at the top needs more explanation. The eCryptFS uses key rings for the key handling. And on Linux, you can manipulate this with the keyctl command. I compile the keyctl command for ARM and run it as root on the phone. With the show sub command, you can list the keys on the key ring in the specified key ring. With the key ID from the output, you can print out the clear test key as root. So this is how clear test encryption key for the SD card. So this is how can you back up your SD card encryption key. One problem solved. Then we will issue the mount command with the normal user privileges, so without root privileges. The eCryptFS _ sig mount parameter shows which key was used for mounting. And Samsung phones, this is the first 8 bytes of the clear test key. So a zero privileged app can have the first 8 bytes of the clear test encryption key, because everybody can run the mount command. It reduces the key length from 256 to 192. It's not a big thing, just a bit strange, because as I said, everybody can run the mount command. And we have live demo for the SD card stuff also.
Yeah, you make combo. Okay, so let's restart Sandy again. Yeah, let's change the phones as well. No, first things first, Sandy. Okay, so I just use the old S3 again.
These modules are work on S4 too, but we should reboot the phone to get it working, so that's why we just switched to already booted S3.
Let me check it. Yeah. Okay, so. Okay, Sandy, and now we go for the SD card option. And okay, I show you this get key file module. It's not a big thing. We just download the EDK _P _SD file from the phone, as Laszlo mentioned. So it's just an ADB pool. It's not magic. Yeah, download the key file. So we just downloaded the key file. We can convert it to John format, and you can use the same John module to crack it. So you saw it 2 times, so I'm not going to show you again because, trust me, it works. So let's go for the keyctl stuff because it's much more interesting. Default values are fine. And yeah, so we just uploaded the keyctl utility, again precompiled and bundled with Sandy. We issued the keyctl show command to get the keyring. And here is the key ID. And we use the key ID with the keyctl command in order to get the clear text SD card encryption key. And we just save it and download it from the phone. So, okay, so we've got the clear text device encryption key. What's the point? Let's say we have a file from an encrypted SD card. Oh, I should make it bigger, I guess. Yeah, so. SD card. So we have a file. It's from an encrypted SD card from this S3 device. And if you want to see the content, we got garbage because it's encrypted, so it's OK. So let's try to mount this file, because we have the encryption key, so we can use it.
Mainly mounting the directory
Yeah.
that contains the file.
Free and from key file, yeah? So as you can see, we just add the given key to the key ring with the key CTI utility, because it uses key rings. And we use the eCryptFS with the eCryptFS underscore sig. And this is the first 8 byte of the clear text key, as you remember. So if we are good, then if I check the SD card folder, it's the same file, but in this case, we can see the content, the very sensitive mail attachment.
It's not important. It's not a home movie.
Yeah, we have another demo for the home movie part. So. OK, so, just zoom out. And I noted the joke with send in the beginning was a bit tough, so now we have a real surprise for you as one more thing. I mean, we have a real surprise.
I have a better thing here. I'm just joking. OK, one more thing. Last year in our presentation, in our database presentation, we have a mobile stuff. Now, in our mobile presentation, we have some database stuff. I know it's a bit far-fetched, but it's fun and it's cool, so you will like it. We are going to show how Oracle stores the database password links, how to store the password of the database links in an encrypted form. With the help of the database links, user can connect to a remote database while he logged into a database. You can create a database link in a way when the username and password is stored in a normal table. So when the user tries to use the database link, he doesn't have to know the username and the password of the database link. This is the old way, how the password was stored. When you can see, yes, you can see. When you can see 05 at the beginning of a hex string in Oracle, you can be sure it is DES encrypted. Just use the first 8 bytes to decrypt it. And the screenshot, you can see how can you decrypt it with Python. Just use the first 8 bytes as a key, of course, except the 05, and the rest as the encrypted password, and call DES, and it will decrypt it. This is the new way, from version 11.203. As you can see, we have a much longer hex string here. This is our Python script. How can you call our Python script to decrypt this log hex string? Just provide the version number and the log hex string as a parameter. The first run failed because by default, SQL Plus, the default command line client for Oracle, prints out only the first 255 characters. But the long hex string is 256 characters long. Fortunately enough, the algorithm is so robust, you can put any hex string, hex character at the end, and it will decrypt it. The algorithm is so robust, the Python script itself is 83 kilobytes long. OK, I'm joking. It is not long because of the algorithm complexity. The algorithm itself, it's fairly simple. It takes only one page. However, there is a 16 kilobyte long constant that is used as a chooser to pick bytes from the long hex string. Then the picked bytes is used to XOR to another constant, which is not a constant, but now let's see as a constant. And the result will be an AES key and the encrypted password. And you can just quote AES to decrypt it. So that's simple. One constant changed, the constant in the XOR, in the XOR operation from version 11 to version 12. The linked $ table that stores the username and password is well protected. Only the sysdba user can access it. So 2 days ago, I said this is not a security vulnerability because the Oracle needs the clear test password anyway to log into the remote database. However, I received an email from Oracle yesterday. They categorized this as a security vulnerability, and they congratulate me and asked for my Python script. I sent them the Python script, and then they answered, OK, thank you very much for your contribution, but please note, the 16 kilobyte constants is Oracle copyright. So I won't publish it publicly. OK, summary. We think it's a good idea to clean up the clear test encryption key and the password from the memory. So we showed you how can you dump the encryption key and the password from the memory of a Samsung phone. We showed you the trust zone, this new magic, is just another security technology that should be used in the right way. We showed you, or we solved the mystery of the SD card encryption of the Samsung phones. And we showed playing with Oracle is always fun. Just don't break copyright. OK, references. These are our URLs. I would like to emphasize the last one, which will be a great book from Paul, my friend. You can pre-order it, about 12C Oracle security. I have some very small contribution in it. And this is our last slide. You can download everything from GitHub except the Python script, the presentation, and please don't try to find me on Facebook.
OK, so basically we have 5 minutes, so we have 2 options. First, I can tell you something more about Sandy, or we can invite the beautiful lady again to the stage. First one or second one?
OK.
Please. In the meantime, I'll tell you something about Sandy. OK, but I know you are here because of this Sandy, not the lady. So,
I think we can leave now.
Yeah, we can leave now. Or you can, oh, no. So, OK, so why I restarted Sandy 2 times? Basically, Sandy, everything is Sandy based on projects. So this is why you must apply this project name parameter, in this case, S3. So let's say the inter-module communication based on the project names. So if I show you the results folder, you may say that every output file generated by Sandy is prefixed by a project name. So this is how the different modules can find the output of another module and use it as an input.
So use a simple project name.
Yeah.
Like the case number, the dates, and everything.
Yeah. OK, so this is why I restarted Sandy when we changed the phone, because S3 and S4 are 2 different projects. So this is the first thing you may know about Sandy. The second thing is, as I said, everything is saved to the results folder. Of course, you can reconfigure it, but as I said, you may leave the defaults on because this is how we tested it. And if you have a DD image, for example, you may put it to the results folder as well. OK, it's kind of strange because it's not a result, but whatever. So put it in the results folder, please. And
The config file.
Yeah, the config file. We have a config file as well. So the main folder of Sandy, there is a config file. We have a config file. So as you can see, we tested Sandy on a limited number of devices. And as Laszlo mentioned, not just the device model, but the given Android version is important as well. So because, for example, the name of the SD card file or the footer offset or other things may change between the different phones and among different phones and Android versions. So if you are able to test Sandy on a Samsung phone with any Android version, it would be great to contribute the given values and put it into the config file, because there are just 4 devices. So for example, this is my previous private phone.
And we bought the S4 together.
Yeah, so we have just a limited number of phones. So if you have a Samsung phone and you are about to play with Sandy, please do it. And please share the results with us, and we can contribute it to the, because Sandy is on GitHub, so we will commit.
Yeah, it's easy to contribute.
Yeah, it's easy to contribute, or you can just send it to
Pull
us.
request
And,
or us.
yeah. So please test Sandy, play with Sandy, whatever.
It's a girl.
She's a girl.
Oh, sorry. She's a girl.
She's a girl. Okay, so we have 2
going to
minutes.
get
If you
emails
have
because of
any
that.
question, please feel free to ask. We try to answer it in English. No questions. You want the lady again? Oh, we have another lady as well. Please. Let's say we have 0 minutes, and you can.
Because we finished.
Yeah,
Yes.
we finished. It's a good day for you guys. Wow.
So thank you very much.
Yeah, thank you very much.